My name is Ajay Jacob, and I am the Director of Projects at the California Dreams Hub. It's my pleasure to invite Professor Austin Minnich to give this California Dreams Technical Seminar for this week. Professor Minnich is the Deputy Director of the Division of Engineering and Applied Sciences at the California Institute of Technology. He's also the Professor of Mechanical Engineering and Applied Sciences at Caltech. He received his bachelor's degree from UC Berkeley in 2006 and his PhD from MIT, and he started at Caltech since then. He is the recipient of the 2013 NSF Career Award, 2015 ONR Young Investigator Award, 2017 Director of Research Award, 2017 Junior Prize from the International Photothermal and Photoacoustics Association, and 2017 Bergles-Rohsenow Young Investigator Award and the Presidential Early Career Award in 2019. Several awards. And Professor Minnich is going to give us a talk on ultra-low noise indium phosphide high electron mobility transistors. Austin, the stage is yours. Thank you so very much.
Great. Thanks so much for the introduction. Thanks to the organizers for the invitation and all of you for spending some of your day with me. I'm looking forward to talking to you today about indium phosphide high electron mobility transistors, or HEMTs, and the limits of microwave noise performance. So just the hub overall is focused on microwave devices based on compound semiconductors, which in the applications are discussed as communications and radar and other things. I wanted to motivate the work today with a bit of a different motivation, which is black hole imaging. This is now a very famous image, which is the first ever image of a black hole from a galaxy far, far away, as they say. And you may know that this image was taken in millimeter wave wavelengths, so around 250 gigahertz or so. And to get this image took tremendous amount of technology, radio telescopes all over the world, the mathematical framework to take those measurements and integrate them together into an image. And one of the really important physical components in all of this effort was the low noise microwave amplifier. That looks like what you see here. These are operated at cryogenic conditions at every radio telescope in the world because they give outstanding noise performance. This is a side view SEM image of a HEMT. So it's a field effect transistor, and it operates by applying the signal to the gate source terminals. Then you measure, to get the amplified signal at the source drain terminals. The reason that these particular HEMTs are so important for low noise application lies in this heterostructure that you see on the right. The origin of the name high electron mobility comes because the conducting channel hosts a 2D electron gas. The dopants are actually located in the barrier just adjacent to the channel. As a result, even when you cool this device, the electrons in the gas remain highly conductive. And in fact, they become more conductive at low temperatures. And that allows you to get this fantastic high frequency and low noise performance down to 4 Kelvin. So we, of course, always want amplifiers to be better, as in lower noise. This is a plot of noise temperature versus frequency. And you can see from 1 to 100 gigahertz, today's amplifiers are something around 4 to 5 times the quantum noise limit, which is the red line. This is at cryogenic temperatures. Above 100 gigahertz, HEMTs tend to be less competitive, and it's for the most demanding applications, low noise mixers are required in front. So for the black hole applications, as well as other scientific applications, we'd like all these noise temperatures to go down. And just for scale, this is a quote that we hear at Caltech: 1 Kelvin in noise temperature is worth $10 million for radio observatories, because the only other option is to make more dishes, and dishes are expensive. So if we can get even a Kelvin improvement in noise, it's tremendously valuable for these scientific applications. All right, so what if we could do that, what would happen? Well, that's the kind of image, this simulated image on the right of what you could see if you could, for example, deploy these amplifiers in space and get even better angular resolution. And this would be pretty neat if we could see this. We can't see it yet, but part of the way to get there is to understand the noise mechanisms of HEMTs and hopefully make them even better noise performance. And so that's what I am looking forward to telling you about today. First, I'll talk about our study of thermal noise under cryogenic conditions. Then I'll talk about drain noise and the role of hot electron transport. And finally, I'll describe our efforts to improve the HEMT fabrication approach via atomic layer etching. Okay, so first up is cryogenic heat transfer and thermal noise. To begin, I want to quickly describe the Pospieszalski model of HEMT noise, which is the predominant model in the field for describing noise in terms of an equivalent circuit. So at the upper left of the screen, you can see the structure of the HEMT, and we can make a small signal model, which includes the noise sources. And these are typically, in this model, attributed to the gate origin. On the left of bottom of the screen, you can see TG, which is T gate, as well as an output noise, which is referred to as drain noise or hot electron noise. And that's described by a parameter TD or T drain. And those two noise temperatures underlined are important because the minimum noise temperature of the device is related to them as shown by the equation. Now in the model, these are just fitting parameters, but over the years, interpretations have been assigned to TG and TD. So in particular, TG has been attributed to thermal fluctuations in the gate metal. TD, on the other hand, has kind of remained a fitting parameter even since 1989, and there's not a universally accepted interpretation. So in the first part of the talk, I'm going to look a little bit more deeply into T gate. And this plot is what originally got me into HEMTs, which is not my training. My training is actually in thermal transport, but the radio astronomers came to me with this plot of noise temperature versus physical temperature, and they were trying to understand the features that they saw, namely that if you use that circuit model, you'd predict the noise to vary with physical temperature as the dashed black line. And indeed, that occurs above about 50 Kelvin or so. But you can see below 40 Kelvin, and particularly below 20 Kelvin, the noise plateaus. And for a long time, there were no really accepted explanations for this. What I did as one of my first efforts in this field was investigate the possibility of self-heating. And in this hypothesis, the power dissipated by the bias applied to the device leads to the gate temperature being hotter than the physical temperature. And if that were the case, the gate would emit more thermal noise than you would predict in the simple circuit model, and then you'd get more noise measured than you predicted. So this was a work that we did now about 10 years ago. And what I'm going to tell you today is how we were able to get more direct evidence that this self-heating is the cause. In the work that you're seeing, we used noise measurements to infer the temperature. What we wanted to do in this study is more directly measure the temperature of the gate. Now, that's not so easy because the gate is half a micron at best for the gate head dimension, and it's buried under tens of nanometers of passivating dielectric. So techniques like IR thermography or Raman spectroscopy are not very straightforward to enable temperature sensing. What we did instead is use Schottky thermometry, which relies on the temperature dependence of the Schottky characteristics of the gate junction to extract temperature under different conditions. So the Schottky thermometry method relies on the temperature dependence of this familiar Schottky equation. And you can see the saturation current IS as well as the ideality factor eta both have a temperature dependence in them. And so you can exploit that to get a thermometry method. So in the first step, you use DC current voltage, or IV, characteristics, as well as microwave S parameter measurements to essentially calibrate these temperature dependencies. And then with that, you can extract the junction temperature under different conditions. For instance, different biases or cryostat temperatures. So before I show you all of that, we can just look at the raw data of what goes into the analysis first. So these are the IV characteristics of a HEMT gate junction in forward bias. In addition, here are the S parameters plotted on a Smith chart. So the different colors are different gate currents, and the different points correspond to different frequencies between 1 to 18 gigahertz. So these are the raw inputs. Now, before we even do any formal quantitative analysis, even just by inspecting these IV curves, you can already learn a lot. So for instance, here's the IV characteristics at room temperature. And we can start with this model and kind of throw out all the complications and gradually add them back in. So to begin, let's ignore self-heating, let's ignore series resistance, and we actually get a pretty decent fit to most of the IV curve. You can see below maybe about a milliamp of current on the y-axis. This equation describes the data really well. Now here's a good example where looking at the small deviations is worth the time, as we'll see. If you look at the right top of the plot, the data don't quite match the dashed black line, although it looks not so large of a deviation. But that deviation is hiding something. Let's improve the model by accounting for series resistance, which we can measure. And if we include that, we actually overcorrect with that dashed dotted blue line. So now we underpredict the measurements. And then finally, we can try to fix that by accounting for self-heating. And if we assume that the junction temperature is linearly depending on the applied power, we get the red line with the R thermal as the fitting parameter, and that fits very nicely. So we conclude that at room temperature, we see self-heating is evident in the data above a milliamp or so, and that the thermal resistance is independent of the bias. Now at cryogenic temperatures, the story is a bit different. So these are now 20 Kelvin IV characteristics. We can see now the region of ideality is quite a bit less, so only up to maybe 100 microamps. If we put back in series resistance, we again significantly underpredict the measurements. But now the interesting thing is if we put back in self-heating with a constant thermal resistance, we get this red line, which doesn't look anything like the data. And so that tells us that self-heating is clearly important, but there's some assumption in the current model for self-heating which is not right. And that assumption is that the thermal resistance is independent of bias. You can clearly see from the red line compared to the data that the thermal resistance, it has to depend on bias to explain the measurements. Okay, so now we can be more quantitative. Using the Schottky thermometry technique, we can extract the temperature rise on the y-axis versus the power density on the x. And at room temperature, we see that it's approximately linear, the temperature rise in the power density, which is expected. And that temperature rise is only kind of maybe a few percent of the base temperature, 300 Kelvin, which is again reasonable at room temperature. Now at 20 Kelvin, the story is completely different. You can see it's not a straight line anymore. There's this curve. And the temperature rise is even a few times that of the base temperature. You can see the maximum, the temperature rise is 50 Kelvin over a base temperature of 20 Kelvin. Now, in the field, this was not expected because if you look up the thermal conductivities of the various materials, typically the thermal conductivity of semiconductors is 10 times bigger at cryogenic conditions compared to room temperature. So it was kind of assumed in the field that self-heating would be negligible at cryogenic temperatures. But clearly the data is telling us that it's very important. And in fact, it's the dominant effect. So to understand how we can reconcile those two viewpoints, we can do a bit more analysis. We can next extract the thermal resistance, which is just the temperature rise divided by the power. That's plotted again versus power density. And you can see again 300 Kelvin and 20 Kelvin results. And you again find that the 300 Kelvin is basically independent of power, but the 20 Kelvin resistance has to change with bias to explain the data. Okay, so now looking to the right of the slide, we can try to understand what mechanism could cause this first by estimating the thermal diffusion resistance from Fourier's law. And the expression for that is given in the box. It's the gate length over kappa approximately. And if you plug in numbers for the gate length, these are all hand-waving estimations, but it gives the scale. You get a number which is 0.5 in these units. And if you put 0.5 on the scale of the plot on the left, it's not even on the plot. It's basically at the bottom at 0. So what that says is that heat diffusion resistance is way too small to explain what's measured under these conditions at cryogenic temperatures. All right, so how to reconcile that? The key insight is that at cryogenic conditions, the heat conduction mechanisms are different than they are at room temperature. So typically we describe heat conduction with the equivalent of Ohm's law, where we have diffusion of heat carried by lattice vibrations. And as long as the mean free path of those lattice vibrations is small enough compared to the relevant lengths, then that's when we get the equation for the diffusion resistance. But at low temperatures, phonons can propagate hundreds of microns or even millimeters without any scattering. And in that case, the transport is what's known as ballistic. The interesting thing about ballistic heat conduction is that the heat flux is proportional to the heat capacity. And if you remember your solid state physics, heat capacity goes as T cubed, the Debye law, at low temperatures. And that means that the thermal resistance, which is the inverse of that heat capacity, goes as 1 over T cubed. That means that the thermal resistance increases very rapidly with decreasing temperature. So if you make a little model just based on that, it really explains the 20 Kelvin data quite well. And so this is compatible with the statement that heat transfer in cryogenic HEMTs occurs not by heat diffusion, but rather by phonon radiation. Okay, so with that key insight, we can make another little model which predicts the gate temperature versus base temperature for different power inputs. And that result is shown on the left. And what it says is that for any practical power input, there's a plateau in the gate temperature and therefore in the gate noise as well. And so this is some pretty firm evidence that the limits of noise performance in part for these HEMTs is really driven by self-heating, and that leads to this noise temperature plateau. Okay, so that's the kind of key finding from this part, is that thermal noise is a fundamental limit to the noise performance of HEMTs. I won't present it here, but we have other papers where we did study how we could potentially overcome this limit with superfluid helium cooling, for example. And the result was that we could not. So this is the statement after a lot of attempts to try to overcome this thermal noise. Okay, now I'd like to go to the second part of the talk. And in that part, we are switching to look at drain noise. This is added at the output in the model. And unlike the gate noise, there really isn't an accepted interpretation of this noise source. There's been various proposals, but I think the community has not yet settled on one of them. So I'm going to present our efforts to give a physical explanation for that noise. And to do that, we're going to do S parameter and cryogenic noise measurements. So the S parameter measurements are pretty straightforward. So we have a cryogenic probe station, which I'll show a picture of in one slide. And we can maintain the sample down to 20 Kelvin, and we use a VNA to send in the signals. The microwave noise temperature is a bit trickier, but it's something we routinely do. And the key idea is you send in different levels of microwave power, and then you look at the amount of power coming out, and through a quantity called the Y factor, which is the ratio of those noise powers, you can get the noise temperature. So here's the picture of this is a home-built probe station in the radio astronomy lab at Caltech. It's a very busy picture, so you don't need to look at everything, but if you look towards the center of the picture, you can see the gold or brass colored locations. So that's where the device sits, and there's a blow up of a device on the right. This is an ohmic 70 nanometer in-gas metamorphic HEMT, which is the device under test. The signals come into the probe station from the left, and then they exit on the right. All right, so here's the data you can get out of this. On the left are the S parameters, again, on a Smith chart. On the right are the measured microwave noise temperatures versus frequency. This is at the bias indicated in the upper left of the figure. And these are the noise measurements that you get versus physical temperature. And you can see going from room temperature to 40 Kelvin, that's about a factor of 5 or so, which is why every radio telescope has a cryocooler on it. And you can also notice that there's the increment by which the noise improves for a given temperature change. It's not uniform completely. In particular, between room temperature and 150 Kelvin, there's a particularly big improvement. And we'll look at that as a kind of a clue later. Okay, so here's the measurement of the noise temperature versus physical temperature. And what we're measuring is known as the T50, which means the noise with 50 ohm source impedance. So with a model that we can create of the device, we can now predict what happens under different scenarios for the drain noise. For instance, if we suppose the drain noise temperature is independent of physical temperature, we can calculate that and see how it compares to the data. That's what's shown in the red. The constant SID means constant output noise power. And you can see it doesn't agree very well. The red is quite different from the black. Another way to say that is that the SID, this output noise power, it has to vary at least somehow with physical temperature, and the amount it has to vary is shown on the right, and it goes from, in these units, 1.5 to maybe 0.6 over that range of temperatures. So it's a factor of something like 2 to 3. Already this is contradictory to some theories for drain noise, so this is definitely a useful clue. All right, the other thing we can do, which is commonly done in the CMOS literature, is apply VDS and then figure out this output noise SID. So this is at 40 Kelvin that you see, and then at room temperature on the right. The shaded region is where we think impact ionization is important, so we can kind of neglect that part. But the rest of the points indicate that there's some dependence of VDS, which we need to explain. Okay, so those are the data. How to interpret them and compare them to a theory. The way that you can do that is calculate what is the thermal noise of a channel when it's under a bias. This was a question that was first posed in the very early days of microelectronics in the 60s by Van der Zeel, who's a well-known name in microelectronics and noise. And they reported these theories of how to do that. And basically you have a VDS across from left to right, as well as a gate potential. And the interesting result is that this noise power, it looks a lot like the Nyquist-Johnson noise expression, except for a gamma factor, which accounts for all the things of the channel being under a bias. Okay, so all that complication is lumped into a gamma. And the interesting thing is that gamma cannot be too different from 1 under the conventional mechanisms included in the derivation. So this is allowing us now to put some theory on those plots. Okay, so in the theory, the noise basically doesn't depend on VDS strongly at all. So that's why it's a horizontal, flat line. It's the dashed red line from the theory. And you can see it doesn't really match the data that great. It gets part of the contribution, but not all. And the same thing for the temperature dependence. It actually gets the trend of temperature dependence reasonably well, but not the magnitude. So the conclusion here is that there's another noise source missing that we haven't included yet. All right, now, just looking at this data, what are the characteristics that noise source is supposed to have or needs to have? Well, just eyeballing it here, if it's approximately independent of temperature, then that dashed dotted black line reasonably fits the measurements. So we can tell already that whatever this noise source is, it has kind of a weak temperature dependence. All right, so looking through the literature, and now this is going back to 60s, 70s, 80s, people did think about this type of problem. And there is a noise source which kind of matches all these requirements, and it's known as real space transfer noise. And the idea is that under the gate of a device, when it's biased, the electric fields are quite big, and they can heat electrons out of equilibrium to temperatures of order 1,000 Kelvin. When that happens, the electrons actually are hot enough to thermionically emit out of the channel and into the barrier. Those two films have very different electrical transport properties, with the channel being highly conducting and the barrier not. And when you have that situation, it's kind of the classic case of what's known as partition noise. And that occurs when there's two paths to the same final contact, but they have different transport properties. So as a schematic example here, if a blue electron becomes a red one by hopping from the channel to the barrier, the conductance of the source to drain instantaneously goes down. And that leads to an instantaneous drop in the current. And vice versa, if an electron hops from the red barrier back into the channel, the conductance all of a sudden goes up. And so when you have these hopping events constantly happening, that manifests as a fluctuating conductance, which then is noise. Okay, so that's the idea of the noise mechanism. The electrons can emit from the channel into the lower mobility barrier in a process known as real space transfer, and that leads to current partition noise. So how might you tell if this is happening? One way is to adjust the properties of the heterojunction, but not change those of the barrier. So particularly of the channel, as we don't change the properties of the channel. And the reason is you want the conducting properties of the channel to not change, but you want to alter the confinement of the electrons in the channel. The way you can do that is actually altering the alloy percentage of aluminum in the barrier. And because a heterojunction requires two parts, if you change the properties of the barrier, you'll actually change the confining potential of electrons in the channel without changing the channel itself. Okay, so that's the idea. We have some measurements which I'll only present very briefly, but we used ungated structures like what you see here. And this is a measurement of noise temperature versus E field in these structures. And you can see that in the blue case, which is a lattice-matched barrier, lower quantum confinement, above some field, these electrons get hot enough to hop out, and there's this rapid increase in noise in the blue symbols. But in the tensile barrier, where the quantum confinement is better, although the initial noise looks like a little bit bigger, you'll notice that it doesn't experience this very rapid increase at the same E field compared to the blue case. So we interpret this as the quantum confinement is able to suppress the hopping of these electrons out of the channel. So this is some evidence that this effect is actually present, and that suggests a path forward to make HEMTs, to manipulate that epitaxial composition. Now, how good could we do if we were able to eliminate that additional hot electron noise source? So this is a plot of the minimum noise temperature versus VDS. The blue symbols are from the model. The red symbols are if we remove this noise source. So you can see in room temperature and 40 Kelvin, something like a 30 to 50% improvement depending on the particular conditions. And for radio astronomy, again, 1 Kelvin is $10 million. So the radio astronomers here are quite excited about the potential here. Okay, so and what we're doing now is making HEMTs and trying to realize that. All right, going on to the last part of the talk. Now I want to turn into, rather than studying the fundamental noise mechanisms, I'm going to talk about new ways that we could fabricate HEMTs that would enable improved scaling and hence improved noise performance. All right, so looking at the side view of the HEMT again. The critical, or one of the critical dimensions of the HEMT is the gate channel separation. And this is a very fine balance where we want the gate as close as possible to the channel to get the maximum transconductance or effectively gain, but we can't get it too close or else the leakage current will be too big, which also undermines noise performance. So that's a very delicate balance, and it does really impose some scaling limits on these devices, especially for low noise applications. So the way that this process is done now is we start with an epitaxial stack and we need to etch into the semiconductor. And over many years, there's some pretty well-known etch liquids, mixtures which selectively etch the different materials. So this is a common way that's done at present. The problem with that is that it leaves behind a pretty low quality damaged region from the wet etching. And you can see it as that fuzzy region just above the nice crystalline semiconductor in that image. And that poor quality region enhances leakage currents, and it also hosts electrical traps, which are very bad for stability. There are other options, for instance, dry etching based on plasma. This is of interest presently for gallium nitride devices. The trouble is that they tend to increase roughness, and they also can be damaging for the semiconductor in terms of trap density. So you can see at the bottom on the right, the initial RMS roughness is 0.44 nanometers. After RIE, it's 0.81, which is probably indicating more traps. So today I want to tell you about an approach that's getting a lot of interest in both nitride and indium phosphide communities, and that's atomic layer etching. And the idea is that rather than having a continuous etch, like what I showed on the previous slide, you instead break the etch up into steps, where each step intrinsically does not etch. But when you combine them together in a cycle, they do etch. So for example, some of the earliest ALE processes for 3-5 semiconductors consisted of exposing InGas to a chlorine plasma that would create chlorides on the surface, which you could then sputter off with a low energy argon beam. And that energy was chosen low enough that it wouldn't hurt the InGas too much, but it would remove the modified layer. And this is now actually done for nitrides. The problem for InGas is that you form compounds like indium chlorides, which are not very volatile, requiring a kind of energetic argon step to remove. And that creates traps. Recently, there's been a lot of interesting developments in what's known as thermal atomic layer etching. And that's where you don't use any plasmas. You just expose the surface to various gases or precursors, and that also can etch. So one really interesting work is where they exposed InGas to HF, which produced those fluorides that you see. You can then use a precursor dimethyl aluminum chloride, or DMAC, which was found to produce etching. And that's a great process. There's still indications that it changes the stoichiometry, which is a little bit of a complicated plot, but the main takeaway is that the stoichiometry changes as the process goes, which may be okay, but it also may not. So we decided to try to advance the chemistry side of things by creating an ALE process for indium gallium arsenide. The first approach is where we tried to kind of mimic the thermal ALE process I showed you, but with using a plasma mixture. The justification is that HF is typically not usable in many commercial tools because of toxicity. When you combine SF6 and H2 in a plasma mixture, you actually make HF in the reactor, and you don't need a source of HF, which is kind of interesting. So we did that, and we produced these fluorides. Then we exposed to TMA, which is based on other related etch processes that have been found. And you can repeat that. And this is a plot of thickness change versus cycle number. A key requirement of ALE is that each half step should not etch, but when you combine them, they should etch. So this is a plot of only TMA, and there's no etching. This is a plot of the plasma step only, and there's really not a whole lot of etching. And then when you put them together, you do see some etching. These are not the cleanest data, but as it turned out, this process had other problems. Namely, it caused significant roughening of the surface if you compare the right plot to the left. So this wasn't so suitable for our purposes. We decided to try another strategy. And that strategy is based on noting a common surface treatment used in MOCVD and MBE fields. In that situation, often you create or you grow a semiconductor, and you might cap it by making an oxide, or just in air it grows an oxide. And then when you want to grow on it, you need to somehow get rid of the oxide. And the way that folks figured out how to do that is using atomic hydrogen at around 200 C. So this is a plot of XPS data before and after that atomic hydrogen treatment. And if you look at the shaded regions in the upper plot, those are basically due to the elements bonding with oxygen. And if you look in the bottom plot, all those shaded regions are gone, which is interpreted as the atomic hydrogen removed the oxide. And this has been very successful for enabling a nice pristine surface to grow another film on top. Okay, so this gives us an idea now. If we just cycle this, we can get etching, very, very precise etching, which will enable us to etch deeper and more precisely for our gate recess etch. All right, so this is the summary of the process. We take oxygen gas, we then use atomic hydrogen. This all is occurring at a pretty high temperature, although we've gotten it down recently. And the chemistry that's happening is probably these formation of suboxides, referred to, or what suboxides means, like gallium-2O or indium-2O. And they're pretty volatile. So when you reduce the initial oxides to those suboxides, you remove those elements. All right, so we were trying to do this in an Oxford ALD chamber with a plasma on it. And the first effort, we simply exposed the chip to the ICP plasma. And what we found from ellipsometry is that the semiconductor was basically getting converted into something else that was not a semiconductor. It was more of a dielectric with a different refractive index. So the key electronic component of the material was damaged. And this was we attributed this to ion impingement. So we had to get a little bit clever with trying to, with the idea that we needed to use this tool for the moment, but we need to also shield it from ions. So you can make a little roof structure where sapphire protects the sample, and you can still get these radicals in. And that worked pretty well. You can see the ion damage, which is the black region at the right image. It's kind of confined to the edge of the chip, but the rest of it looks pretty clean. Now, when you do this, we can look at these half-cycle thickness changes versus number of cycles. So when you only expose to oxygen, basically nothing happens. When you only expose to the H2 plasma, a little bit happens, but not much. But when you do both of them together, you get a measurable thickness change. So that's the key requirement for ALE. The other requirement is after enough exposure of either component, you should not get an increase of etching. So that means the etch saturates with enough exposure to the different reactants. So that's known as a saturation curve. So here I'm plotting the etch per cycle on Y versus now here the oxygen gas exposure time. And you can see after a certain amount of time, there's not additional etching. And roughly for the hydrogen exposure time, you see basically the same thing within the uncertainty. There's a point at the right, which is a little bit, unexpectedly lower, but we attribute this to probably the ion damage due to the longer exposure time. But basically within the uncertainty, we do see the same thing for the hydrogen. So this basically says that this is indeed atomic layer etching. All right, and then as a kind of last check of do we understand what's happening, this is the XPS for gallium and indium and arsenic. If you look at first at the center and right images, just like I showed before in the plots from the reference, you see the green shaded region, which is the oxides, are essentially gone in the bottom panels, which is after ALE. If you compare vertically, top to bottom. Returning to the left image, which is the gallium and gallium oxides, we can see they're significantly reduced, as evidenced by the green area. Compare the top and bottom, the green area. They're not gone completely though, which is also actually expected just because the gallium oxides are generally more stable than the other indium or arsenic oxides. But overall, we've removed a significant amount of the oxygen as evidenced by XPS. So finally, we want to look at the surface characteristics of the etched surfaces. So on the left is the AFM scan of the as-grown wafer, which is very, very good, RQ of 0.1 nanometer. This is after wet etching a few nanometers of the semiconductor, and you can see it's clearly rougher. And this is after ALE of order of 100 cycles or so. And you can see it's essentially indistinguishable from the as grown. And so this is very important. The low roughness is it's a reasonable indicator that the surface is electrically good, although not guaranteed, but it's an indicator. And the roughness also impacts the transconductance. If the surface is smoother, the transconductance in general will be higher. So there's a lot of positive indications for the surface quality of this ALE. Okay, so we've developed a HEMT process, a fab process at Caltech. We're now really working to integrate the ALE process into the overall HEMT flow so that we can achieve this gate recess etching performed with ALE. And so that's really the active research going on right now. All right, so this is kind of approximately how we do the flow. The only difference, if you're kind of expert in this, is we need a hard mask for the atomic layer etching because it's in this plasma, or rather it has these hydrogen radicals which will attack the resist, so you need a hard mask. But otherwise, it proceeds pretty similarly to what you might be familiar with. All right, so to sum up, there's a lot of applications for HEMTs and microwave devices that we hear about in the hub. And we're also really interested in going from the left to the right, going from a fuzzy black hole to a really nice resolved black hole where you can see these photon rings at the center where light is trapped for millions of years. It's really pretty neat stuff. There's a lot of technology, but one of the key components is lower noise HEMTs. So with that, I'd like to thank the students who did so much work here, particularly Mette was responsible for the ALEs, and all the students have just done a great job. I'd also like to acknowledge the funding and the DREAMS Hub for just being a great resource, and it's been a great experience. So with that, I'll stop, and I'm happy to take some questions.
Thank you, Austin. Great presentation. Let me open to the audience. Is there any questions? You can raise your hand and take the mic and you can ask. Okay. I have a question, Austin. So I have a couple of questions actually. So one of them is with respect to the ALD etching and the roughness that you have studied. Did you also, so in addition to the gain noise that you measured, did you also do 1/f noise that can characterize where the defects and where the thermal noise would be coming?
Yes, this is an active research topic for us. We are actually building a 1/f noise measurement setup to characterize the gain stability. The prediction is that when you use ALE, that noise should be substantially improved, by a lot is the expectation. A lot meaning maybe factor of 10, as determined by the trap density.
Yes.
So we're very interested in that, and indeed we are actively working to characterize that. So please stay tuned.
Okay. Yeah, I have a couple of questions, but I think Ben, Professor Ben has raised his voice.
Yeah.
Ben.
Can you hear me okay?
Yes, we can.
Okay, great. Yeah, thank you. This is exciting. I'm sorry I joined late, but it's a nice talk.
Thank you.
On the ALE, the etching, you mentioned about indium chloride, and then you do differently and so on. But indium chloride, if I remember, will kind of evaporate. Indium chloride is like salt. It's very, a bad, hard material. But if you heat it up, the surface to like 180 degrees or so, it will kind of dissolve or dissociate or dissolve. So you could actually avoid that problem, right?
Yeah, it's certainly possible. You're right. There are papers that we did come across where if you get to something like 200 C, you can desorb the indium chlorides.
Mhm.
Based on our experience, exposing InGas to a plasma, just because there's a plasma potential and the ions in the plasma will be accelerated towards the semiconductor through that, even that was enough to cause damage that manifested electrically. And so we've moved to now actually completely thermal process where there isn't this plasma. But I think you are right. In principle, one could desorb these chlorides if it was about 200 C or hotter.
Okay. Yeah, a lot of time, depending on the etch rate, the surface gets hot as the time goes on, but
Yeah,
it's usually a good idea to do it at a stable temperature. All right, thank you.
yeah, thank you.
We have one other question from Jamie.
Hello, can you guys hear me?
Yes.
Oh, well, first, very nice talk. And I just had just a curiosity question. If you have the surface and you were to do like an inert implant just to amorphize, like say, one or two monolayers, and then you were to regrow them back, then you could also minimize your defects. Is that something that theoretically would be interesting or no?
So I guess it depends how the top layers are amorphized. There's data going back to Bell Lab days where if you have ions impinging on a semiconductor at some energy, you can electrically detect that damage like tens of nanometers down. So even if like the atoms are only displaced at the very top level, there's other kind of electrically relevant defects that are created like far further down. So I guess our philosophy was we want to be very careful if ions are involved because we really do care about the traps. So that makes sense. So yeah, mainly the point is the ions can induce damage, not necessarily just where the atoms are moved, but even farther down.
Okay. Thanks, Austin. I have another question, which is, I saw some of these plots, but I probably missed it, which is gate length scaling versus the thermal noise or the gain noise that you would probably generate, as well as the thickness of your channel versus the gain noise. You might have plotted it. How is that, especially with respect to the cryogenic temperatures?
Yeah, everything ends up in F max in the equation. So yeah, in the sense like if you scale, you have to scale everything proportionally. Gate length, gate channel separation, and then all of that ends up in F max, and that's what you need to improve the noise. Is that answering your question? Yeah.
Oh, okay. What you're essentially saying is you did that study and it's all proportional to the gate length is what the noise is proportional to the gate length is what you're trying to say, what you're saying, or scaling.
Well, it's proportion. So it depends on like gate source capacitance, the other small signal parameters, which themselves, yes, they depend on gate length, but they also depend on gate channel separation, for instance, because of GM. So the different geometrical and other parameters combine together in a specific way. So like maybe to answer another way, if you just decrease gate length, you won't necessarily improve noise. You have to do things proportionally.
Oh, okay.
Yeah.
Okay.
Yeah, you have to scale everything harmoniously.
Just as Lennart's law is talking about in digital world, in CMOS world.
Right. Yeah. There's right in CMOS. There's different types of scaling laws, and it's the same in compound semiconductors. There's scaling laws, and if you don't scale things harmoniously, then it won't manifest. Yeah.
Okay.
Yeah. In terms of noise, in the low noise world, there's a lot of interest in low power because of quantum computing. So their noise is important, but also power is important because of the cooling requirements in the fridge. So there, they actually scale the gate channel separation, but not the gate length. And that allows them to operate the device at lower power. However, the noise is not improved, but that's okay.
Yes.
Yeah, depends what you want.
You know, there is something called zero temperature coefficient, which is if you plot the IC, T, current capacitance versus the temperature, there is at some particular temperature, if you scale the temperature from room temperature to the extreme low temperature that you are trying to highlight to 20 degree, there is some inflection point where there is a crossover that happens. Were you able to see such crossovers?
I don't know if we plotted exactly that quantity.
Okay.
We certainly, like kind of in the first part of the talk, we certainly see around 20 Kelvin, for example, right? There's a clear change from like higher temperature to lower temperature phenomena with regards
Yeah.
to heat dissipation. You know, clearly we see that. Yeah, it's not quite the same thing as
but that's not really the zero temperature coefficient. Is where when you plot the IV versus the temperature.
Yeah, it's
So IVC versus the temperature.
Yeah, it's not quite the same thing.
Okay.
Yeah, I don't know if we've explicitly plotted that particular thing.
Okay. Thank you, Austin. Is there any more questions? Okay. If not, let's thank Professor Minnich once again. Thank you so much. It was a great presentation.
Thank you. Yeah, thanks for listening. Appreciate the opportunity.
Amy, can you? Oh, Amy, can you put the posters? Okay. On October 3rd, the speaker is still being decided. On October 10th, we have Professor Wong from UC Riverside will be giving the talk. So stay tuned. Thank you all. Thank you for attending.